In this problem, we're given a mass concentration of 10 milligrams per cubic meter for carbon monoxide, and we're asked to express this in units of parts per million. So we're given a mass concentration C, and we're trying to go to a volumetric concentration or molar concentration Y. So the approach is to find Y. We know that we can do that using this equation to convert, that Y is equal to C divided by the molecular weight. Because we're at standard conditions, we simply multiply that by 0.0245 cubic meters per mole. So now I can go ahead and make my substitutions. Our concentration is 10 milligrams per cubic meter. Let me divide by 1,000 milligrams per gram to convert that to grams. We'll divide by the molecular weight of carbon monoxide, which is 28 grams per mole. And then we multiply by the 0.0245 cubic meters per mole. This gives us 9 times 10 to the minus 6. Now if you look at the units here, grams cancels with grams, milligrams cancels with milligrams, cubic meters cancels with cubic meters, moles cancels with moles. So we have no units. But if we go back and look about what those cubic meters are, we would see that in the 10 milligrams per cubic meter, that cubic meter is cubic meters of air. And the cubic meters over here in this conversion is actually converting the moles of carbon monoxide to cubic meters of carbon monoxide. We have cubic meters of carbon monoxide. And so now we need to convert this to ppm. And so to get ppm, we multiply by 1 million parts per million. So it's multiplying by 1, which is like multiplying the number 0.02 by 100%, which is 1, to get 2%. And so if I do that, I have Y is equal to 9 times 10 to the minus 6 times 10 to the 6 ppm, and this is equal to 9 ppm. In our second example problem, we are now given the ozone concentration in units of ppb. This is, again, a volume concentration or molar concentration, and we're asked to convert it to units of milligrams per cubic meter. And this is in Blacksburg on a hot summer day with a temperature of 35 degrees Celsius and atmospheric pressure of 97% of sea level pressure. So this is not standard conditions, and so we need to convert from Y, ppb, to C, milligrams per cubic meter. The first thing we're going to do is that we have this Y is equal to 80 ppb. In the previous example problem, we solved for Y and we got a number of just 9 times 10 to the minus 6, and then we had to multiply by 1 million ppm to get it to ppm. So now we do the opposite of that, where we can divide. So what this really means is this is divide by 10 to the 9th ppb, or we can see this as 80 parts per billion. It's 80 times 10 to the minus 9. What are the units here? Really, it's cubic meters of ozone per cubic meter of air. And this gives me really 8 times 10 to the minus 8. So what I did, again, is I just took my 80 ppb, and I divide by 10 to the 9 ppb. It's like dividing by 1. And then we get this same thing, 8 times 10 to the minus 8. So that's my Y. And now we need to calculate C for non-standard conditions. So I can take my general equation for y as a function of c and rearrange it and solve for c. I get that c is equal to y times the molecular weight times p over RT. And so if I make my substitutions here, I have my y, which is 8 times 10 to the minus 8. My molecular weight of ozone is 48 grams per mole. My pressure is 0.97 atmospheres. My R is 82.05 times 10 to the minus 6 cubic meters atmospheres per mole Kelvin. And my temperature is 35 degrees Celsius or 308 Kelvin. Now if I run that through the calculator, I get 1.5 times 10 to the minus 4 grams per cubic meter of ozone. I was asked for it in milligrams per cubic meter of ozone, so I multiply by 1,000 milligrams per gram to convert, and I get 0.15 milligrams of ozone per cubic meter of air.